In this video, what we'll be doing is we'll be solving this simply supported beam using Ansys Workbench, and then we'll be plotting this shear force and bending moment diagram for this simply supported beam. Also, we'll be finding the maximum deflection. Now here, this beam is made up of 3.5 meter length with three spans of 1 meter, 1.5 meter, and 1 meter each. Then the cross section of this beam is 100 by 100 mm. Young's modulus is given as 210 GPa and Poisson's ratio is 0.27. Now since again here the forces which are applied are static forces, we will have to perform this analysis using static structural, right? So from analysis system under Ansys Workbench, we will choose static structural. We will drop it here under project schematic. Let us name this as 1D beam. All right, let us name this as 1D beam. And at this stage, let us save this project. To save it, just click on this save project icon. Save it in a safe location somewhere in D drive. Name it. I will name it as 1D beam. With this, we will save this, and then the first step we have already completed here. We have selected the type of analysis which we want to do. It is static structural. Under second step, we need to define our engineering material. We need to give the inputs for this engineering data. So what we will do is we will click here on this. Click here to add new material. There we will type the material as steel. You can give any name. Then here again, since the analysis is linear, material is isotropic, we will take isotropic elasticity from linear elastic, and then we will drop it on the steel. It is asking us for Young's modulus and Poisson's ratio. We can give it these values from here. The Young's modulus is given as 210 GPa and Poisson's ratio is 0.27. So since it is 210 GPa, it is 210 gigapascals, it is 210 multiplied by 10 to the power 9 pascals. So we have to enter it as 210 E9. E9 stands for 10 to the power 9. Just press enter, and then Poisson's ratio will enter it as 0.27. Once this is done, we have defined our material. Close this tab and then click on save project. Once this engineering data is given to the software, now we have to create a geometry. Right click on it. If you have the geometry with you, you can even import it, or you will have to create a new geometry here by clicking on this design modeler icon. We'll click here on this new design modeler geometry. It will open now the design modeler. Now we have to do this sketching on some plane. So we'll do it on this XY plane. For that, just right click on this and then say look at. I will adjust this origin to my convenience the way I want. I will adjust it. I'll slightly zoom out of this so that my dimensions are coming proper. Once this is done, then I will go to the sketching. I will take this line option and make sure that these alphabets like P and C are visible. Those are basically different types of constraints. If you cannot see this alphabet, again you have to go to constraints, and then you just need to come down here, and then finally what you need to do is click on this auto constraint and make sure that global and cursor is on. Once this is done, again go back to draw, take this line, and then we have to draw three different segments, right? I'll click here first segment, make sure that this H alphabet is visible, which tells us our line is horizontal. Click here, and then again make sure that you can see this P, you can see this P letter, P alphabet. Click here and then again create one more span, then click at the end point of this sketch and then create one more sketch. Basically this three sketch represents the these three segments. All right, now we need to give the proper dimensions to these three segments as 1 meter, 1.5 meter and 1 meter. To do that, we'll go to dimensions, click on general, and then just click on this line and then drag it down. Similarly, click on this line, drag it down, click on this line and drag it down. Here we need to now define these dimensions of H1, H2, H3, which are nothing but 1 meter, 1.5 meter and 1 meter. So for that, just click here on H1, enter 1 and then press enter. Similarly, H2 is this dimension, which is nothing but 1.5 meters. Press 1.5, press enter. Then H3 is finally 1 meter. Press 1 and then press enter. So this completes our sketch. If you want to zoom, if you want to fit this to the screen, you can just press F7 from your keyboard. It will fit to your screen. So this completes our sketch. Now, as we have been discussing, Ansys will not understand our sketch, or while converting this into elements and nodes, Ansys will not understand this sketch. We need to convert it into line body, right? It has to be in terms of some form of a body. So in this case, since this is a one-dimensional sketch, we have to convert it into line body. For that, we can go to concept, and then we already have sketch. So we'll be creating this line bodies from sketches. So select these lines from sketches, then select this line, press Control, select this sketch, press Control, select this sketch, and then say apply. Once you say apply, this everything will be highlighted, but the body is not been created yet. You can see here it is 0 part and 0 body. To create the line body, just right click on this line and then say generate. Now a body has been created, right? A line body has been created. If you just expand this, you can see that a line body has been created. But the problem will be if you click on this line body now, it is asking for cross section because we have not defined any cross section for this line body. Because here the cross section is made up of 100 mm by 100 mm rectangular cross section. Therefore, we will have to define the cross section properly. To define the cross section, you can go to concepts and then go to cross section, select this rectangular. Okay, now we'll be defining this dimensions. We need to define B and H, which are nothing but 100 mm and 100 mm each. Now these units are in terms of meters, right? The units are in terms of meters. To convert that into mm, you need to go to units and then select here mm. Then you can enter your dimensions as 100 mm by 100 mm because our cross section is made up of 100 mm by 100 mm dimensions. So this is my cross section. Once you create the cross section, make sure that you assign it to the line body, because although we have created this cross section, we have not assigned it to the line body. For that, you need to select this not selected, click on this not selected, you will get this drop down arrow, click on that and then assign this rectangle 1. Now we have assigned a proper cross section to our line body. Alright, if you just want to confirm that we have really assigned a cross section to this line body, what you can do is go to this view and then click on cross section solids, which will show you that this cross section has been assigned to the line body. This completes our geometry. Alright, then at this stage what we'll do is we'll just save this geometry and then I will just minimize it. I will not close it yet, I'll just minimize it, and then we need to now go for step 4, that is to create a finite element model, and subsequently this step number 5, 6 and 7 will be taken care in this step itself. So just right click on this model and then say edit to open the mechanical window. It is showing here, it is starting this mechanical. Once this mechanical opens, you will be able to see our beam in terms of line body. This white line is nothing but our beam in terms of line body. If you want to check it in terms of a cross section, you can go to view and then click on this cross section solid. You will be able to see it in terms of its cross section. But I would prefer at present to watch it, to see it or to look at it in terms of line body. So I will put off that and then I will click on this Z to align it along XY plane. Now if you just click on this geometry and then click on this line body, you will see that the material which is assigned to this line body is still structural steel. Ansys by default always gives this material structural steel to any of our bodies. But we had defined a proper material for this project, and that is steel, right? So what you need to do, click on this structural steel, you will see this arrow, click on that and assign our proper material, that is steel. So once we assign this, now it has taken this material properly for this line body. So this is done. Cross section we have already seen, a proper cross section has been also assigned. Now our next step is to mesh this body, to discretize this body basically. So we will convert this line body in terms of elements and nodes, which this finite element method will understand, right? It will not understand even this line body as such. So for that, just right click on this mesh and then say generate mesh. Now what it will do is the software will create a automatic mesh. Alright, it has created some automatic mesh. It doesn't look that bad. In order to watch this in terms of nodes and elements, what you can do, you can go to this view and then uncheck these thick shells and beams. Once you uncheck these thick shells and beam, you can see these elements and these black dots are nothing but the nodes. If you want to refine this, if you want to make finer mesh, or if you want to create more number of elements and nodes, what you can do is you can click on this mesh and then click on this sizing and then change this default size to whatever size you want. I mean not here element size, under element size you can give whatever size you want. Alright, and then if you click on this mesh, you will get here many mesh control methods. Like if you click on the mesh, you will get this different methods like refinement and sizing and so on. But for this simple analysis, these options are not required. If at all, if you want to refine this mesh, you can directly give some dimensions of the element size, dimensions for this element size. We'll come back to it later on. If in case if we are not getting proper results, we'll come back and we will refine our mesh. At this stage, most of the things are done, but now comes the most important step under this analysis, that is giving the proper boundary condition. That will be done under this static structural head. Right click on the static structural, and then this menu will appear here, like giving loads and supports. Be very careful while giving the boundary conditions, because this is a simply supported case, and in simply supported case we all know that the beam which is like this is simply supported at one end, it is supported on a hinge, and on the second edge it is supported on a roller. Right, we are all aware of this. So basically what happens is that at this end it is its translational movements are totally restricted. That means it cannot move in x direction or y direction whatsoever, but it is free to rotate about this hinge. Right, it is very free to rotate along the z axis. About the z axis it is very free to rotate. And what about at this end? What about at this end? At this end, it is free to move in x direction, right? Since it is on roller, since this is on roller, it is very free to move in x direction, but it cannot move in y direction. Definitely, it cannot move in y direction. So, and again, then it can very easily rotate about the z-axis. So, z-axis is the axis which is coming out of this plane. So, about that axis, it can very easily rotate because it is on hinge. So all this we need to take care while giving the proper boundary conditions. All right. In fact, these boundary conditions which I have shown you now, these boundary conditions are called as, which are related with the displacement, are called as essential boundary conditions. All right. But here this applied forces, they are called as natural boundary conditions. Okay. So we need to properly define all these boundary conditions under static structural. So for that what we will do is we'll click on the static structural, then we will click on the supports, and then now which support to be given. Now out of all this support, here I will choose a simply support for this end. What is this end? Again, this end is where all its translational motions are restricted, but it can rotate. And then since I have taken this simply support, what this simply supports means is that if I show you all the different types of boundary conditions in Ansys, see here there are so many types of this essential boundary conditions, like fixed support, displacement. Fixed support is usually given for cantilever beams, right? They are fixed at one end, but simply supported beams are not fixed at one end. So these are the different types of boundary conditions which we can give. Now I am talking about this simply support. Now this simply support means that it prevents all the translations, but all the rotations are free, and this is exactly what we want at this end. Right, at this end, I'm talking about at this end, we require the rotational moment, but all the translation motions are restricted. So that is why I am taking this simply support here. So once you take this simply support, it is asking for geometry. I will have to choose this node. Now I mean this point, but it is not allowing us to choose this point because our selection is on edge. I have to go to vertex selection. So click on this, and then now it will allow you to choose this point. Click on that. It will change to green color. Then say apply. So at this end we have applied a simply support. Okay. Now what about at this end? At this end we cannot apply simply support, because in simply support it restricts all the translation motion. But here at this end it is free to move about x-axis. So for that I cannot apply, because of that I cannot apply this simply support again at this end. What I will have to do, I will have to go to supports and then take remote displacement. First let us apply this remote displacement at this end. I will click this point, it will change to green color, and then I will say apply. Now what this remote displacement does is that, look here, it gives us control of all these three translation motions and three rotation motions. Now in this case this end is free to move in x direction, so this should be free. but its movement in y direction should be 0, that is translation motion in y direction should be 0, and its translation motion in z direction should be also 0. So this will be free, this will be 0, this will be 0. Its rotation about x-axis is 0, its rotation about y-axis is also 0. But it should be free to rotate about this z-axis, right? So this will take care of all this. So therefore, here at this end, for a simply supported beam, we have to go for remote displacement. Now, if you click on the static structural, it will show us these two boundary conditions, this essential boundary conditions. This side it is simply supported, this side there is a remote displacement. The next thing is we need to apply the natural boundary conditions, that is these two forces at these 2 points. So what I will do is I will click on this static structural, and then I will go to the loads, then I will click on forces, and then I will just take my cursor here, and it will show me one point. Now it is showing me this point because while modeling this beam, I had made sure that I don't draw a continuous line of 3.5 meters, but I had drawn it in terms of the segments, right? I had drawn first line, then I had drawn the second line, and then I had drawn the third line, if you remember, right? And then because of that, it is giving me this ready-made points here at these locations, all right? So we will take advantage of that. I will take my cursor here at this point, I will click on it, it will change it to green color, then I will say apply. And after this, what you have to do is go to this define by, click on this vector, and then click on this and change it to the components, so that we can define our force in y direction. Now the force which is applied here is 2 kilonewton, which is nothing but 2000 newton, but it is in downward direction. So therefore, while entering, I will have to enter minus 2000. The reason is because it is acting in downward direction. If I enter here plus 2000, it will act in the upward direction. Similarly, we need to apply a force here at this point. So therefore, again go to the loads, click on force, and then take your cursor somewhere here, and then it will highlight this point. Click on that, it will change to green color, then say apply. Again click on this vector, change it to components, and then similarly I need to define this y component now, in this case as minus 4000 Newton. So this will be minus 4000 Newton. Okay, so now if I click on the static structural, we'll get to see all our boundary conditions. These two are essential boundary conditions, these two are natural boundary conditions. So at this stage, we are ready to solve this problem. Before solving, I will save it once, I will save our project once, and then after saving, I will right click on this solution, and then I will ask it to solve. So this is the second phase, that is the solution phase. Earlier, whatever we had done was a pre-processing phase. Now it has solved our problem without giving any error, which is a good sign, but it is not showing us any result. That is because we didn't ask software what kind of results we want. For that, you need to right click on this and then go to insert, and then click on beam tools, which will give you different types of results which are associated with the beam. We also need to find the shear force and bending moment diagram, and then also we need to find the maximum deflection. To find maximum deflection, you can just right click on this, go to insert, and then go to beam tool, go to deformation, and then click on directional deformation, because we want the deformation in this direction, in the y direction, right? So therefore we need to choose this directional deformation, and the orientation we have to change it to y axis, because I want the deformation in y direction. All right, also I want to plot the shear force and bending moment diagram. For that, right click on solution, go to insert, and then go to beam results, and then click on shear moment diagram. All right, now once you click on shear moment diagram, it will ask you path. Now this is basically what it is asking us, along which path we want to plot the shear force and bending moment diagram. For that, we need to specify this path properly. And how to do that is, you need to go back to this model, right click on it, say insert, and then construct geometry. So we need to choose this option, construction geometry. Again, right click now on that construction geometry, go to insert, and then click on path. Now it is asking us how I want to create a path. What we will do is, this path type from 2 points, we will change it to edge, so that because we already have this ready-made edges, just click on these edges. Now it is on point selection, change it to edge selection, and then click on these edges, press Ctrl and select all these edges, and then say apply. So it has taken basically all these edges. All right, it has taken all these edges. So we have defined the proper edge. Now we'll go back to this shear force, total shear force bending moment diagram. Click on this path, click on this drop down menu and select this path. So basically now it will give us the shear force bending moment diagram along this path. Now we need to be careful. What we are asking to the software is to give us total shear force and bending moment diagram, but truly speaking we want the directional shear force bending moment diagram in y direction. So for that what we need to do is just click here and then click on directional shear force bending moment diagram, and then you can take this option. All right, that is the deformation or the deflection in y direction and the moment about z axis. Right, so this is what we want. So once we choose this, I think we have asked for everything. Only thing is, if you want to find the locate the reaction forces at this end and at this end, that also we can do. For that you can just right click on this, go to insert, and then you need to go to probe and then click on force reaction. All right, so force reaction we want it at this end, which is a simply supported end. So I will click on this, so it will give us the force reaction at this end. Let us also find the moment reaction at that end. So we need to go to probe and then click on moment reaction, then click on this simply support. So we will be getting the force reaction and moment reaction at this end. Similarly, we need to find the force reaction and moment reaction at this end. For that again right click on the solution, go to insert, probe and then force reaction. Give the boundary condition as remote displacement, because this side we had given remote displacement, right? So it will give us the force reaction at this end. Similarly, we will also look at the moment reaction. So go to the probe, moment reaction and then give boundary condition as remote displacement. So basically now this is all what we are asking to the software to show us. These all results it will show us. For that, you need to right click on the solution and then say evaluate all results. It will not solve again, but it will evaluate all these results. It is giving us some error because this is basically a limitations of software. We cannot do anything about that. So almost everything is ready for us. Let us click on the shear force and bending moment diagram and let us see how it is plotted. So if I click on this directional shear force and bending moment diagram, it is showing us the shear force diagram as this. Maximum is 3.43 kilonewton approximately, and this is 2.57 kilonewton, which is minimum along the length, right? From here to here is our first span, from this point to this point is our second span of 1.5 meter length, and from here to here it is the third span of 1 meter length. The bending moment diagram, it is showing somewhat like this, and the deformation or the deflection, maximum deflection is at 1833 mm from this side. All right, at a distance of 1.8 meters approximately, we get a maximum deflection of 2.347. The minus sign shows that it is in downward direction. Now what I had done was I had just roughly plotted this results of this beam by the hand calculations, and I had got a similar kind of diagram. All right, I had got a similar diagram. If I go here, I had done all these calculations. And I had obtained a similar diagram. All right, now here only thing is, according to my sign convention, I got this as negative shear force, this as positive shear force, because I use this sign convention. Ansys might be using some different sign convention, just opposite sign convention to this, and therefore the software is getting this as positive and this as negative. Never mind, but we can see that it is changing its direction here at this point, and therefore here we are getting the maximum bending moment. So all this we can validate, all our knowledge of MSOL we can use, we can apply, and we can validate our results. All right, if you want to look at the directional deformation, even that you can do. You can just click and you can see that the maximum deformation is here, which is minus 2.347, which it clearly showed us in this diagram also, right? Okay, then we can check the reactions at this end. The force reaction, we are getting it as 2.57 kilonewton in upward direction. Of course, in x direction, along x direction and along z direction, it will be 0 because there are no forces acting in those directions. So definitely the reaction will be 0. The moment reaction at this end, it is showing as 0, because definitely since we had allowed it to rotate freely about z-axis, it is showing as 0. The reactions, the moment reaction is 0. There cannot be any moment reaction because we had allowed it to rotate freely about z-axis. Similarly, I can watch this force reaction at this end. It is showing it is showing as 3.43 kilonewton, and if you see, even I had got the same reactions, right, by manual calculation, by hand calculation, 2.57 and 3.43. And then if we talk about the, if you look at the moment reaction, it is showing moment reaction as, it is showing a very small value. These values are almost 0, but why it is not showing exactly 0 is that because our mesh is a very coarse mesh. If I refine this mesh, if I make it a more finer mesh, I'm sure this will go to 0. This reactions in over x-axis about y-axis, this also will go to 0. Let us just try it. What I will do is I will click on this mesh, and then this I will go to the sizing and then element size. Let us take the element of 10 mm each. Then the earlier mesh will be obsolete. So since I have changed now the element size, I will have to right click on the mesh and then say generate mesh again. So it has generated a very fine mesh. If you just zoom in, you can see that this is our element and these are our node. All right. So this distance from here to here, it is of 10 mm. All right. So it has generated a very fine mesh. It has created a very fine mesh. With this, if we just solve our entire problem again with the new mesh size, I'm sure it will give us the better results at the as a moment reactions. If I now click on the moment reaction, we'll be able to see that okay, it has almost tending to 0 now. It has increased, right? This value has increased, I feel. Yes. So as and when, as we are increasing the mesh size, as we are making it more and more fine, definitely our results improve. All right. The directional deformation has also, now it is almost same. Okay. So this is how we can plot the shear force and bending moment diagram for a simply supported beam, provided we take a proper boundary conditions here. We give a proper boundary conditions. In case if we had not asked for the directional shear force and bending moment diagram, if we had just kept it as a total shear force and bending moment diagram, I'll just evaluate these results. It will, what it will show us is, it will show us just the quantities or just the total shear force and bending moment. Here it is not showing us the negative, this side it is not showing us any negative values, right? Or this side it is not showing us any negative values. Even this it is showing us positive, because here since we have asked for a total shear force and bending moment diagram, it is just showing us the final values without considering any directions. But if I want a directional bending shear force bending moment diagram, I will have to change it to directional shear moment diagram about y-axis and z-axis, and then again I will say evaluate results, and this will give us a proper results in y direction. So this is how one can solve a simply supported beam on Ansys Workbench.